Okay, so same idea, principle, but now we have a definite integral where we're going to use substitution to solve. And so again, you need to figure out what u is. This is not an integral that we can just go straight in and take the integral antiderivative of. And so let's choose u. I had mentioned that sometimes if you have things underneath a radical, more than one term, that's usually a good way to start. Also to think about what that derivative is, and is it going to cancel out with other values of that variable we're integrating with, in our case r, which it will. So we're going to choose u to be 1 minus r squared. And then we differentiated both sides. So we get du equals, well, the derivative with respect to r of 1 minus r squared is negative 2r dr. We then solved for dr. And in this case, we get dr is equal to, so divide both sides with it by negative 2r, we get dr is du over negative 2r. The problem is that these bounds are for our value of r, not for u. And so there's two different ways that we can do this. We can keep those bounds in terms of r, and then go back in and substitute like we did before, or we can change our bounds now. And I think it's easier to change our bounds now. And so let's find out. We have a value when r equals 0. So let's find u when r equals 0 and when r equals 1. So if I go back in here and I plug in 0 for my r, I would get that then u would equal 1. So in here I got u is 1. And then I need to go back in, same idea, and I have to go in and I have to plug in 1 for r and figure out what u is. So find u when r equals 1. Well, I get 1 minus 1 squared. 1 minus 1 is 0. So then u is 0. Let's go back. This is r. And let's plug in square root. Well, we had chose that radicand 1 minus r squared to be our u value. And our dr value, well, that's the du all over negative 2r. So we can clean this up before we take the antiderivative. Notice we have an r in the numerator and r in the denominator. And if we wanted to, we can use rules of integration. We can pull out that coefficient in front. I noticed, I don't know if you noticed this, but notice that my bound on the bottom is bigger than my bound on my top. And we had talked about ways that we could change that. We had seen that there was a rule that says if you have the integral of b to a of f of x dx, this was the same thing as taking the negative and flipping these bounds, a to b of f of x dx. So let's do that. We're going to use that rule. I'm going to flip these. We're going to change our sign, which is minus then. But I'm also bringing out a negative 1/2. So minus 1/2 of my integral. My bounds are flipped now. So u equals 0 to u equals 1 of the square root of u. But in order to integrate that, we want that as a power. So we can write that as u to the 1/2 power. And then we're just left with du. Okay, so negative of negative 1/2 is 1/2. We can now go ahead and we can take the antiderivative of u to the 1/2. So that is where we added 1 to our exponent. So 1/2 plus 2/2 is 3/2. divide by our new exponent, but it's a fraction, so let's multiply by the reciprocal, which is 2/3. This is a definite integral. We did not have to add that plus c. And then we wrote the vertical line, and this represented that we were going to evaluate this from 0 to 1. So we look at the upper bound, plug that into our antiderivative, minus plugging in our lower bound to our antiderivative. Because we changed our bounds here to be in terms of u, we don't have to go back and do that extra step where we go and do substitution. So that's why I kind of like it better. And then you don't forget. But let's go ahead and now evaluate this. I notice here too, my 2's cancel. To me, it's easier when I'm plugging things in for my variable and I have a rational exponent to rewrite that as a radical. So this u to the 3/2 power, the denominators tell me I'm taking the square root of u. It would be easier if I pull the cubed outside of the radical. Especially if I'm dealing with big numbers, it's not a huge deal here. And again, I'm evaluating that from 0 to 1. So plugging in our upper bound first, we have 1/3. We have the square root of 1 and then cubed. Minus 1/3 square root, plug in 0, quantity cubed. Well, square root of 1 is 1, 1 cubed is 1, and so this gives us back 1/3 minus 0, which is 0. So we have 1/3 minus 0 is 1/3. So we're looking now at the definite integral. Our lower bound is pi6 to our upper bound of pi3 of the quantity. So inside the parentheses, we have a 1 minus cosine of 3t. And then in your parentheses and outside the parentheses, we have sine of 3t. And then we're integrating with respect to t, so dt. So you need to choose what you're gonna let your u value be. I notice, sine, when I take the derivative of 1, it usually gives me the other one except for the negative in front of one of them. It's better that you take it what's inside the parentheses in this case, because then it's just going to be one term there. And we won't have to worry about things not canceling. And so let's choose your u value to be 1 minus cosine of 3t. So derivative of u with respect to x is du equals derivative of 1 is 0 minus, so I'm going to have to use the chain rule here. So the derivative of cosine, well, derivative cosine, again, I think of it, remember derivative is slope, cosine comes down. So I think of that, that's negative sine. So that's going to be a negative sine as my outer of my inner 3t. But I also have to multiply by the derivative of the inner, and the derivative of 3t is just 3. And then I'm going to put this dt. So I have du is equal to, well, negative and negative is positive. And let's just pull this 3 out front. So this will be 3 sine of 3t dt. So we want to go in and plug in what we did for our substitution. And so right now we have, these are t equals. So let's ignore that for now. We have u. This is u. We have sine of 3t. And now let's write dt. So dt we can get by dividing by this 3 sine of 3t. So dt equals du all over 3 sine of 3t. So we have that u sine of 3t, and now we're going to rewrite what dt is, and we just saw that dt is this. So we're going to write du all over 3 sine of 3t, which is nice because we can't have any variable t left in our integrand, and so these sine 3t's cancel. So we can pull out, if we wanted to, this is like a 1/3 in front of our integral u du. So integrating u is really easy, but let's first, instead of keeping our bounds in terms of t's, let's rewrite what what t would be. U would be, so u is equal to 1 minus cosine of 3t. So if we look at u of pi 6, that would equal 1 minus cosine, that should be a 3t. I don't know why I put 3/2. Cosine of 3 times pi 6. So this is equal to 1 minus, well, notice that 3 pi 6, that's the same thing as pi halves. Cosine of pi halves, cosine's your x value, unit circle, pi halves is at the y-axis, positive y-axis, that's going to give us 0. So when we have t is pi 6, we get that u is equal to 1. So do the same thing. Now let's look at pi thirds. So let's look at u of pi thirds. So that would be 1 minus cosine of 3 times pi thirds. Okay, so 3 times pi thirds, that would make it, now we're really looking at 1 minus cosine of pi. Well, pi, that gets us to the negative x-axis, so that gives us 1 minus, that's -1, which is giving me back 2. So when t was pi thirds, u is 2. Okay, so now we can take the antiderivative. Let's bring down our 1/3. Antiderivative of u, add 1 to the exponent is 2. Divide by our new exponent of 2. And we're evaluating this from 1 to 2. So this is the same thing as 1/6. We technically can pull that coefficient out and just evaluate this u squared from 1 to 2. So plug in our upper bound first, then minus our lower bound. So this would be 2 squared, which is 4, minus, now plugging in 1 squared, which is 1. So we have 1/6 times 3, which is equal to 2. Okay, so now we're taking the definite integral between 1 and 9, so integral from 1 to 9, of t times the square root, and underneath the radical is 4 plus 5t, and then dt. So there's more than one term underneath that radical, and so I'm going to choose my u value to be this 4 plus 5t. Differentiate both sides, so we get du equals 5 dt. And then divide both sides by 5, we get dt equals du over 5. So notice that when I go back in and I substitute, I still have this t in here, and I don't want that. And so I still have to go and manipulate, and this is how we do it. We go back in and we choose, or go back to what we had chosen u to be, and we're going to need to solve for t. Because if we do that, then we have t as a function of u, and then we'll just have u in that integrand. And so to solve for t, I would subtract 4 on both sides. So I get 5t equals u minus 4. Divide both sides by 5. I get t is equal to u minus 4 over 5. And so we can go back in here and replace that. So this is integral of t, which we just said was u minus 4 over 5 times the square root of u. But let's just rewrite that as u to the 1/2 power du over 5. So now it's looking much nicer, and I can almost integrate. We can pull out this 1/25. This is 1/5 times 1/5 outside of the integral. And we can also distribute that u to the 1/2 power and use rules of exponents. So u to the 1st power times u to the 1/2 power. Adding my exponents, so 2/2 plus 1/2. So that's u to the 3/2 power. And then minus 4 times u to the 1/2 power. So 4u to the 1/2 power. So we can now either change our bounds or wait till the end. Let's change them though. And if we change them, I'm going to first let t equal 1. So if we go in here and plug in 1 for t, I get 4 plus 5 times 1. So I get 4 plus 5 is 9. So I get u is equal to 9. So my bottom bound is 9. If t is 9, so plugging in 9 here, 5 times 9 is 45, and 45 plus the 4 out there is 49. So my u value is 49. So going ahead and taking the antiderivative, so let's bring down our coefficient of 1 over 25. And then we're adding 1 to our exponent. So this is going to give me u 3/2 plus 2/2. I'm adding my 1 as 2/2. So 3/2 plus 2/2 is 5/2. But dividing by 5/2 is the same as multiplying by the reciprocal, 2/5. Minus 4. So add 1 to our exponent. So 1/2 plus 2/2 is 3/2. And dividing by 3/2 is the same thing as multiplying by the reciprocal, which is 2/3. And we're evaluating this when x is 9 to x is 49. Okay, so I would probably first rewrite these as radicals. And then I would go in and plug in my numbers. And so I can pull down my 1/25. This is the same thing as 2/5. So this is u. This 2 is telling me I'm taking the square root of u. It's easier to raise the square root to the 5th power instead of taking u to the 5th power and taking the square root. but they're both equivalent. Minus, so 4 times 2 is 8, all over 3. And then we have the square root of u, and then that's all going to be cubed. It's all from 1 to 40, or 9 to 49. Okay, so we first have to plug in the top bound, 49, wherever we see a u. So we have 2/5. We have square root of 49, which we know is 7. And 7 is raised to the 5th power. Minus 8/3 square root of 49, which is 7, and 7 cubed. Minus, put parentheses because there's more than one term in here. We have 2/5. We have the square root of 9. So the square root of 9 is 3. And we have 3 raised to that 5th power. Minus 8/3 square root of 9, which is 3. And 3 is cubed. Okay, let's see. We're gonna need to, where's my calculator? Seven to the 5th power, and I'm thinking that maybe we're gonna need a common denominator. So 7 to the 5th. That is 1,000. It's actually, that's 16,807 times my 2. Oops. Shoot. Times 2. That's going to give me 33,614 all over 5 minus, let's put it over 3. So 7 cubed, that's 343. And that times 8 gives us 2,744 minus, so 3 to the 5th power is 243. 243 times 2, that's 486. All over 5 minus 3 cubed is 27. 27 times 8, that's 216. Let's distribute this negative right now. So this would actually be a plus. So plus 216 all over 3. So we need a common denominator. So I can see that that's 15. So I would multiply this first piece by 3 over 3. I would multiply the second piece by 5 over 5. This one by 3 over 3. This one by 5 over 5. So I have 1 over 25. My denominator here is going to be 15. And so just to save time, I'm just going to put it all in at once. So 3 times 33,614 plus 5 times 2,744. Actually, that's not a plus. It should be a minus, right? Like I was just telling myself I need to be careful what I'm putting in here. Then we have another minus. So 486 times 3. Plus 216 times 5. Oh no. And now it's saying syntax area. Darn it, I don't know what, I just did a error saying syntax error, which means I missed something and then we have to. So this, when you multiply that all out and sum or subtract, you get 86,744. And so this is really 86,744 all over 25 times 15, which is 375. And we can either reduce it or rewrite it as a decimal. That's the answer. Okay, and so I just checked to see if that's the format they wanted the answer in, and that's how they had it. And there was no errors because that was what the answer was. So we're almost done with all the material for this course. We'll finish up on Tuesday with area bounded between two curves or multiple curves, even extending it to finding the area based off of the y-axis, not the x-axis, to help us sometimes to find area. Then we will review next week on Wednesday and Thursday for your second Zoom test, or in Zoom test. That's going to happen that following Tuesday. Then we have 2 more days of class that we'll review for the final, which is on the 24th.